Hi, welcome back to Educator.com. Today we're going to talk about solving exponential and logarithmic equations. At this point, we have a good understanding of how both exponentiation and logarithms work. However, we haven't seen much about how to solve equations involving them. For example, how do we solve something like e to the 2x minus 3 equals e to the 5x minus 12? Or log of x minus 2 equals 1. We haven't really talked about how to do that. We briefly touched on it in the final example in the last lesson, but now we're going to really explore it. We'll go over two different ways of approaching such equations. First, we'll discuss how we can use the one-to-one property, and then we'll see how we can apply the inverse property for more complicated equations. Make sure you already understand how exponents and logarithms work. The previous few lessons explain this stuff in detail, explain how all these things work, their properties, so make sure you've got an understanding of that before you try to get into these equations. While you might be able to understand it, it'll make a lot more sense if you've already got a grasp on how exponents and logarithms work, what their properties are, so then you'll really be able to throw yourself into the equations. If you don't have a good grasp of that first, make sure you've watched those lessons previously because they'll really help out for understanding this lesson. All right. Notice that the exponential and logarithmic equations are both one-to-one. Different inputs imply different outputs. If we put a different value into the function, a different output always will come out. We can see this in the graphs because both function types pass the horizontal line test, right? If we cut an exponential function's graph with a horizontal line, it's only going to intersect at a maximum of 1 point. This means it is a one-to-one function. If you want more to talk about a better understanding of one-to-one functions, you want to check out the inverse functions lesson. Same with logarithmic functions. If we cut at any place with the horizontal line, it will only intersect one time. Thus, they are one-to-one functions. For any input, there's only one output. For every output that can come out of it, there is a unique input that creates it. As an example, let's consider some specific numbers. Like if we wanted to see 3 to the 4th equals 3 to the something, what could go into that box to give us 3 to the 4th? Well, if we think about it for a while, we'll probably go, well, there's only one choice to go into that box. It doesn't make sense for there to be anything else. The only other thing that could be on the other side of the equation is also 3 to the 4th. The only thing that's going to make 3 to the 4th with a base of 3 is 3 to the 4th, right? So 3 to the 4th, the only thing that can go inside of this box is a 4. Similarly over here with log 5 25 equals log 5 something, the only thing that could possibly be in there, if we think about this for a while, we'll go, well, the only thing that could make any sense to go inside of that box is a 25, right? It wouldn't work any other way. There's nothing else that we could take log base 5 of and get the same value as log base 5 of 25. So the only thing that could go in those boxes is the number on the other side of the equation. This is because they are one-to-one. It's this one-to-one property. Since we've got an input of 4 over here, and it gives us an output of 3 to the 4th, 81, we know that the only other input that's going to be able to do that is no other input. It is 4 is the only input that can give us 81 as our output. So the same thing must be here. It's one-to-one. If an input gives an output, the only input that can give that output is that original input. There's no other input that is unique to the output. We call this the one-to-one property, and it says if a base of a is raised to x, and we have that equal to the same base a raised to y, then it must be the case that x equals y. Similarly, if we've got log base b acting on x, and we know that it's equal to log base b acting on y, then we know x equals y. And notice that in both of these cases, the base has to be the same on each one. We've got a to the x and a to the y. We've got log base b and log base b. Log base b of x, log base b of y. We've got the same bases in both of these cases. And that's why we have this one-to-one property kick in. We know that x has to equal y in both of these situations. All right, with this property in mind, we can now solve equations where we have an exponent or logarithm of a single base on both sides of the equation. For example, if we've got e to the 2x minus 3 and e to the 5x minus 12, well, since we've got the same base on both sides, we know that 2x minus 3 has to be the same thing as 5x minus 12, otherwise we wouldn't have equality. So we know 2x minus 3 equals 5x minus 12, and at this point we go about it just like we're solving a normal algebra equation. Add 12 to both sides, so we get 2x plus 9 equals 5x. Subtract 2x from both sides, we get 9 equals 3x. Divide by 3 on both sides, we get 3 equals x. If we want to check it, we can plug in our 3 equals x, e to the 2 times 3 minus 3 equals e to the 5 times 3 minus 12. So we have e to the 6 minus 3 equals e to the 15 minus 12. So e to the 3 equals e to the 3, and that checks out just fine. Same basic idea over here, log base 7 of x plus 5. And let's move the other log 7, 2x minus 3. So we'll add log base 7, 2x minus 3 to both sides. So it will now appear on the right side, log base 7 of 2x minus 3. At this point, we know that what's inside of both logs has to be the same thing. So they're both log base 7, log base 7. So we know that they must be taking logarithms of the same object. X plus 5 and 2x minus 3 must be the same thing. Otherwise, we couldn't have equality. So we have x plus 5 equals 2x minus 3 by this 1-to-1 property. We can add 3 on both sides. We'll get 8. So x plus 8 equals 2x. We can subtract by x on both sides. We'll get 8 equals x, and there's our answer. And if we wanted to, we could check that one the same way. The inverse property. Previously, we've talked about exponentiation and logarithms. If they have the same base, are inverse processes. If they are applied one after another, they cancel each other. They cancel out. So if we have natural log on e squared, well, since natural log is just the same thing as log base e, and it's operating on something that's base e to the 2, then the log base e here and the e cancel out, and we're left with just 2, so sure enough, 2 equals 2. That's the idea of what's going on there. Same thing over here, 5 as our base, raised to the log base 5 of 125. They cancel out, and we get 125. That's how this stuff's coming out. If you want a more in-depth exploration of this, check out the previous lesson, Properties of Logarithms, where we'll actually prove this stuff and see why it has to be the case. We call this the inverse property. So log base a of a to the x is equal to x, and b to the log base b of x equals x. So we've got this cancellation. If we wind up having the same base like this in log base and then exponent base, or in exponent base and then log base, we'll cancel out and we'll just get the thing that at the end. So in this case, x here or x here, we wind up getting out of it. Solving by inverses. So with an equation or inequality, we can do algebra. Now, algebra is just applying the same thing to both sides. We're doing the same operation, whatever it is. When we first learned to do algebra, we just used simple arithmetic, things like addition, subtraction, multiplication, or division, right? What we just saw in the previous thing when we were solving after we used these special properties. But as we learned more in our work in algebra, we realized we could do more than just apply simple operations on both sides. We could even do more complicated things like squaring both sides or taking the square root. We realized that as long as we're doing the same action to the left side and the right side, we're doing the same thing to two things that are equal, we know that it's going to remain being equal even after the action goes through. So by that same idea, we can also make both sides of an equation exponents or take the logarithm of both sides because we're doing the same action to both sides. The equality is still based in it. So if we've got wavy stuff equals loopy stuff, then we know A as a base for wavy stuff is going to be equal to A as a base for loopy stuff, because A to the something on the left equals A to the something on the right, and we were told that left side and right side are the same, so it must be the same still even when they're working as bases for something else, when something is a base underneath them and they're now exponents. Similar idea, if we were told that wavy equals loopy, then we know that log base B of wavy must be the same thing as log base B of loopy. We're applying the same action, whether it's turning them into exponents on some base or we're taking the logarithm of some base of both sides. We're doing the same action to both sides, so we've got this equality still holding. Combining this idea with the inverse property allows us to get rid of exponent bases or logarithms that are in the way of solving an equation. So for example, if we've got log of x minus 2 equals 1, remember, if it's just log, then that's the common log, so it's log base 10 of x minus 2 equals 1. So what we can do is we can come along and raise both sides with a 10 underneath them. So we're not raising them to the power like squaring them, we're actually causing this sort of like base, this exponent base, to erupt underneath them. So we've got 10 to the log base 10 of x minus 2, and that's going to be equal to 10 has erupted underneath the 1. All right, so at this point we've got the inverse property, right? We're solving by inverses, so we've got 10 log 10. So these cancel out, and the x minus 2 just drops down, and we get x minus 2 equals 10 to the 1 is just 10. So now we just solve it normally, x equals 12, and there's our answer. Similar idea going on over here. 3 to the 2x equals 7. Well, let's get rid of that base of 3. That's sort of getting in our way. So we'll take log base 3 of 3 to the 2x, and that's going to be equal to log base 3 of what's on the right side, so log base 3 of 7. Log 3 on 3 to the 2x, those will wind up canceling out, and the 2x will just drop down, so we'll have plain 2x equals log base 3 of 7. Now, if we want to figure this out with a calculator, log base 3 of 7 is still correct, but if we want to figure it out with a calculator, if we actually want a decimal version, we'll have to turn it through change of base. So let's take natural log. I like natural log. So natural log of 7 over natural log of 3. Remember the change of base formula that we talked about in the previous lesson. X equals, now we're dividing by 2 on both sides, so it'll show up in the denominator 2 times the natural log of 3, which will wind up working out to approximately 0.8856. Now notice 0.8856, that's approximate, so it's not the exact answer. This is actually the exact answer. Once we have to calculate it through with natural log of 7 and natural log of 3, we wind up getting something that's very, very close, but it's no longer precise because we're having to cut off some of the decimal places. And if we wanted to, we also could have used any other base. We could have used like log base 10 of 7 over log base 3. Log base 10 of 3, common log there. So we would have had log base 7 over 2 times log of 3. So log of 7 over 2 times log of 3, which would wind up coming out to be the same thing when we used a calculator on it. And this would also be just as equally a correct answer. A useful property, one particularly useful property of logarithms is this ability to bring down things. If we have log a of x to the n, then that's the same thing as if the n had been in the front, if it was n times log base a of x. So we can bring down exponents with any logarithm. This means we can use logarithm bases that we have on our calculators, right? That might be convenient for us sometimes. So remember, e is the same thing as natural log, 10 is the same thing as log without a number on it. So if we want, we can just start off by taking natural log of 3 to the 2x equals natural log of 7. So at this point we can bring down the 2 to the x. It comes down to the front by this property up here. So we've got 2x times natural log of 3 equals natural log of 7. So 2x equals natural log 7 over natural log 3, or x equals natural log of 7 divided by 2 times the natural log of 3, which is the exact same thing that we just had on the previous slide. So the thing to notice here is that we have two different ways of doing this. We could go about it by using the change of base, or we could go about it by just using this property that we can bring down exponents. Sometimes it'll be more useful to use the bringing down the exponent property. Sometimes it'll be more useful to do the change of base. They'll both wind up working out. It's just sometimes one will be a little bit more work than the other, and you'll get a feel for which one you want to use as you work on this stuff. Many of the properties we've discussed about exponents and logarithms can be useful in solving exponential or logarithmic equations. If the problem is complicated, try to figure out if you can first simplify it with some of the various properties we've learned. We've learned a lot of properties by this point about how exponentiation works, about how logarithms work, and sometimes by combining stuff or breaking stuff apart, it'll make the problem easier to do, and we'll see some of that in the examples later on. Extraneous solutions. While solving these equations, it's important to watch out for extraneous solutions. An extraneous solution is a value that appears over the course of solving, but isn't actually a solution. That if we were to try to use it, it would just fail or cause our equation to break apart or not work or not be defined for some reason. So easiest way to see how this works is to just see an example. So let's look at this. If we've got natural log of x squared minus 2 equals natural log of x, by the one-to-one property, we see that x squared minus 2 has to be equal to x. Alternatively, if we wanted, we could put e's underneath it and just cancel out both of them. So inverse or one-to-one property both wind up working as ways to look at this. So x squared minus 2 equals x. Hey, at this point, looks like we're used to using, looks like the polynomials we're used to solving from that section. So we move it over. X squared minus x minus 2 equals 0. So we can factor that. We get x minus 2 times x plus 1 equals 0. We solve both of those, so x minus 2 equals 0, x plus 1 equals 0. We get x equals 2 and x equals negative 1. Now, if we go back and we try to work this out, if we plug in x equals 2, things are pretty reasonable. We get natural log of 2 squared minus 2 equals natural log of 2. So this is natural log of 4 minus 2 equals natural log of 2, and then natural log of 2 equals natural log of 2. Hey, that's perfectly reasonable. But if we try x equals negative 1, we'll see some problems very quickly. So natural log of negative 1 squared minus 2 equals natural log of negative 1. And as soon as we see this right here, we have red flags, right? Because why? What's the problem here? You can never take the logarithm of a negative number. So as soon as we see natural log of a negative number inside, we know this is not possible. We can't take the natural log of negative 1. We can't have logs of negative numbers at any point showing up. So this is an extraneous solution. It's something that appeared over the course of solving because we turned it into this quadratic form, and in the quadratic form it was a solution. But up here, in the original form that we have, it fails to be a solution. It can't be a solution because we wind up having this logarithm of a negative number, so we knock it out. It's an extraneous solution, and our only answer is x equals 2. So it seems at first like we've got two answers because we're solving a quadratic, but as we work our way through the quadratic, we realize, oh, if we were to actually plug this in and try it out to see if it works as a solution, it would cause the whole thing to blow apart. So we wind up seeing it can't actually be used as a solution, so it's called an extraneous solution. Something that appears over the course of solving, but can't actually be used as a solution. So we have only one out of this, even though at first it seemed like there'd be two. All right, ready for some examples now. First one, solve for x exactly if we've got 3/7 x plus 2 and 49 over 9 to the x minus 2. So we look at this and we think, well, we could take logarithms of both sides, we could bring down our exponents, but things are going to get pretty messy. We'll have to actually figure out what the logs are of 49 over 9 and the log of 3 over 7, and we'll have to work out a bunch of numbers. It's going to get really, really ugly. We could work it out that way, but we'd wind up having approximations because we'd be taking the logs of these numbers and they'd come out to be decimals, so that won't wind up working in the end. But if we look at it, we might realize, hey, 49 over 9, there's a connection to 3/7, right? Well, if we want, we could rewrite this as 9 over 49 to the negative 1, right? And then we might realize, hey, 9 is just 3 squared, 49 is just 7 squared, still all to the negative 1. So we can pull out the 2's, and we've got 3 over 7 to the negative 2. Hey, that's what we started with on the left side, so we can use that one-to-one property. So we take this fact here, we can swap them out. So same thing still on the left side, 3 over 7 to the x plus 2 is equal to, we swap out 49 over 9 for 3 over 7 to the negative 2. So we've got 3 over 7 to the negative 2 to the x minus 2. Well, that's going to be equal to 3 over 7. We can bring that negative 2 out by the property of exponents. It'll multiply everything that's already out there, so we have to have that in a quantity as well. So we've got 3/7 x plus 2. At this point, we can use the one-to-one property because we've got the same base here and here. So we have x plus 2 equals negative 2 times x minus 2. X plus 2 equals negative 2x plus 4. Add 2x to both sides. We get 3x, subtract by 2 on both sides, and we get 2, and we get 3. Oh, whoops, sorry. We now divide by 3. We don't divide by 2. That'd be going the wrong way. Divide by 3 on both sides. We get x equals 2 over 3. And there's our answer for x. And if we wanted to, we'd plug that in and check, use our calculator, wind up working it out. We'd get decimal answers that wind up being the same thing. We'd see, oh, that wound up working. So you could check this by using a calculator if you wanted. You could do a check, and you'd have 3 over 7 to the 2/3 plus 2 equals 49 over 9 to the 2/3 minus 2. You'd have to use a calculator to wind up working this out, but if you did, you'd wind up getting decimal answers that were very, very, very close. Actually, they should be exactly the same because we solve for x exactly. The only problem might be if your calculator has just a little bit of slop in it, but they should get decimal answers that are well within, like, 5, 10 decimal digits of each other, and so you'll wind up seeing that, hey, it checks out when you use your calculator. Or you could also just work through each of these and then use the properties of exponents, and you can see that it is exactly the same thing. Two ways to do it. Solve for a exactly if we have log a cubed minus log a squared equals 2 minus log a. All right, so let's use the properties of logarithms to bring some things together, simplify things a bit. Remember, we've got subtraction here, so subtraction of logarithms is the same thing as division inside of the logarithm. So we've got a cubed over a squared equals 2 minus log of a, not base a. Now, the only issue we'd have is, what if a was equal to 0? Well, if a was equal to 0, we'd already have problems because we'd be taking log of 0, so we don't have to worry about that. So we know that a is not equal to 0, so we're good there. We know that a is not equal to 0, so we can do this cancellation. We don't have to worry about that. Log a cubed divided by a squared, well, we'll get just log of a because a cubed over a squared will cancel 2 of the a's on top. We'll be left with just 1. 2 minus log a. At this point, we can add log a to both sides, so we'll get log a, and now there's 2 of them because we added and they're of the same type, right? So log a plus log a is 2 times log a equals 2. At this point, we can divide by 2 on both sides, and we get log a equals 1. We want to know what that is. Well, remember, log is just common logarithm, so it's base 10, so we can raise both sides to the 10. So that cancels this out, and we've got a equals 10 to the 1, which means a equals 10. Great. If we wanted to, we can check this. So as a check, we've got log of 10 cubed minus log of 10 squared equals 2 minus log of 10. Log of 10 cubed comes out to be 3, right, because it's base 10. So what do you have to raise 10 to get 10 to the third? Well, you have to raise it to 3. Same idea over here. Log of 10 squared is just 2 equals 2 minus log of 10. Log base 10 of 10 is just going to be 1. 1 equals 1. Great, checks out. All right, third example. Solve for x to 4 decimal places. 5 to the x plus 4 equals 11 to the 2x. So we could write this as log base 5 acting on 5 to the x plus 4, and then log base 5 on the other side as well, acting on 11 to the 2x. So since we've got log base 5, and exponential base 5, they cancel out, and we've got x plus 4 on the left side. On the right side, we see that we've got 2 to the x raised here as an exponent, so if we want, we can bring it out to the front. So we've got equals 2x times, and then our remaining log base 5 on 11. All right, so at this point, we can divide by 2x on both sides because we want to try to get our x's together. So we can, or actually better yet, we can subtract by x on this side, and we'll get 4 equals 2x times log base 5, 11, minus x. Now at this point we can see, hey, there's an x here, there's an x here. We can pull out the x's, and we'll get 4, pull out the x's, x times 2 times log base 5 of 11 minus 1. We can divide this over. So we have x equals, dividing over, we have 4 divided by what we're dividing over, 2 times log base 5 of 11 minus 1. We can use the change of base formula. X equals 4 over, because we probably want to be able to use a calculator, and lots of calculators can't do log base 5. So 2 times log base 5 of 11. So let's go with natural log, just because I like natural log. So natural log of 11 over natural log of 5 minus 1. Now, that guy looks kind of ugly, and he is. He's going to take some work through a calculator, but you work it through with a calculator, and you'll get that that's approximately equal to 2.0204 once you round it down. So there you are. Another way to have done this would have been to take the natural log of both sides. We could have taken natural log of 5 to the x plus 4 equals natural log of 11 to the 2x, and this would be true with any base. We could be doing this with the common log as well if we wanted. So we can bring down our exponent, so we'll get x plus 4, remember as a quantity because it's the whole exponent, times the natural log of 5 equals 2x times the natural log of 11. At this point we could move the natural log of 5 over, and we'd have x plus 4 equals 2x times the natural log of 11 divided by the natural log of 5. It's over the whole thing, but we can also just compact it into that one thing. And then if we want, we could move the x over as well, and we'd have 4 equals 2x times natural log 11 over natural log 5 minus x. Now we do the same trick, pull out our x's. We get 4 equals x times 2 times natural log of 11 over natural log 5 minus 1. We divide that over, and we get 4 over 2 times natural log 11 over natural log 5 minus 1 equals x, which is the exact same thing that we had when we did it by using log base 5. So really it's just a question of, are we prolonging the change of base or causing the change of base to sort of happen as we take a log in a different base. So two different ways to do it. If you don't wind up realizing this x trick, where the fact that we've got x here, and that we can pull them both out to the front and get x at the front, you can also just work this out sort of through a bit more arithmetic and, working at the thing, moving things around. So you can eventually get it. You could also just do it by evaluating what is log base 5 of 11. You could figure out what is log base 5 of 11, get that down to like 8 decimal places, and then multiply that by 2x, and you could work it out, just work with a whole bunch of decimal places for a while and solve for what x is, and then just, cut it down to 4 decimal places. So that's another way to do it. There's a bunch of different ways that you can approach problems like this. Just, remember all the properties that we've talked about and just work through it and pay attention to what you're doing. And then at the very end, check your work. Do a quick check, and you do a check that 5 to the 2.0204 plus 4 is equal to 11 to the 2 times 2.0204. And in fact, you'll wind up finding out that they come out to be very, very close. They'll wind up being off after like the 5th or 6th digit because there was a little bit of rounding error. We did, after all, only round to 4 decimal places, and it just keeps going forever. But beyond that little bit of rounding error after like the 5th or 6th digit, you'll wind up being they'll be really, really close to being exactly the same. So you'll see that it checks out that you do have the right answer. Fourth example, solve for t exactly. So we're back to solving for t exactly. So we can't really use these numerical methods that we've been working out with a calculator. So we need to figure out something clever here. So the problem here is we've got 2t and t. It's not just the same thing happening up there. And then we've also got this confusion from the 12, right? If the 12 weren't there, we could just move them over and we could use the one-to-one property. But we've got this problem where we've got this 2t minus 4t equals 12. Well, let's try moving things around, see if this looks like something we're used to. 4 to the t minus 12 equals 0. At this point, we might have this aha moment. We might realize, hey, this looks an awful lot like a polynomial, like a quadratic polynomial that we're trying to solve. We realize that this is squared, this is to the 1, and this is to the nothing. This is the constant. So we realize that 4 to the t is kind of like the x that we're used to. So let's say 4t equals u. We'll do this as a u substitution. We'll replace something complicated with something simple, this nice u. So if it's 4 to the 2t, it's now going to be u squared, because u squared would be 4 to the t squared, which is the same thing as 4 to the 2 times t. Minus u minus 12 equals 0. At this point, really easy to solve, right? We see u minus 4 times u plus 3 equals 0. Great, that makes perfect sense because u times u squared, plus 3u minus 4u, that's our minus u, negative 4 times positive 3, negative 12, checks out. So we solve each one of these independently. U minus 4 equals 0, so we get u equals 4. Now what is it? Because we're actually solving for t, right? We're not solving for u, so we replace with 4t equals u, so we've got 4 to the t equals 4. Well, there's only one thing that's going to wind up giving us that. It must be 4 to the 1 there, so we've got t equals 1, right? So t equals 1 is one of our answers. U plus 3 equals 0, so we've got u equals negative 3. We swap out for 4 to the t equals negative 3, and at this point we realize, oh, that's madness, right? There's no possible way that 4 to the t can equal a negative number, right? There's no number we can raise 4 to, no real number we can raise 4 to that's going to give us a negative number. So this way lies madness, so we knock it out. No possible answers there. So our only answer is t equals 1. It seemed like we were going to get this answer, but then we realized, oh, that's not possible. If we want to check it out, we plug it in as a check. So 4 to the 2 times 1 minus 4 to the 1 equals 12. 4 squared minus 4 equals 12. 16 minus 4 equals 12. Indeed, that is true, so it checks out. Final example, solve for x exactly, then give an approximation. So we've got the x that we're looking for is in the denominator. We don't like things stuck in the denominator, so let's multiply it on both sides. So multiply by the natural log of 2x minus 3 on both sides. So we get 4 equals 2 times natural log of 2x minus 3 on both sides. We can distribute the 2. 4 equals 2 times the natural log of 2x minus 3. The thing we want to figure out is it's like we're solving for natural log of 2x, and then later we'll crack the log. But for now, let's just figure out solving for natural log of 2x, and then we can crack the log. So we see 3 on the minus 3 here. We add 3 to both sides. We get 7 equals 2 times, oh, whoops, haha, made a mistake. Important thing to notice. It's 2 times natural log of 2x minus 3, so it's 2 times negative 3. It's not minus 3, it's minus 6, right? So I have to always be careful with distribution because it can catch anyone, including me, including your teachers. You always have to watch out for distribution. So add 6 to both sides, we get 10 equals 2 times natural log of 2x. We divide by 2 on both sides. We get 5 equals the natural log of 2x. We now raise both sides to the e. So e to the 5th, e to the natural log of 2x. Since these are the same base, natural log and e, they cancel out, and we've got e to the 5th equals 2x. So we've got that e to the 5th over 2 equals x. That's our exact answer, right? E to the 5th over 2. Now, e is this complicated irrational number. We can't really, turn it into, it's not exactly a decimal number, but sometimes we want to have a decimal approximation because that makes it easier for us to work with things. So e to the 5th over 2 is the exact answer. That's what it is precisely. But if we want an approximate answer, e to the 5th over 2 winds up being approximately 74.207. Great. Now, if we want to do a quick check, we can do a numerical approximation where we try plugging it in using a calculator. So we'd have 4 over the natural log of 2 times, replace our x, which we know is approximately 74.207 minus 3. You work that through with a calculator, and you wind up getting approximately 1.99999, and then it winds up changing after that. But that's really, really close, so we know that this checks out numerically. We've got that close to being exactly 2, so we see that numerically, because remember, there is some rounding error when we get an approximation. So with that little bit of rounding error, we're still extremely close, so we know that that's a good answer. If we wanted to, we could also work it out and show that it winds up being a precise answer as well, that e to the 5th over 2 is going to be equal to precisely what x has to be. We can check by plugging that in. 4 over the natural log of 2 times e to the 5th divided by 2 minus 3. So 2 times dividing by 2, they cancel out. So we've got 4 over the natural log of e to the 5th minus 3. E to the 5th minus 3, e to the 5th is going to wind up being, so we've got 4 over natural log of e to the 5th has to be 5, because what do we raise e to, since natural log is base e? What do we raise e to get e to the 5th? Of course, we raise it to a 5 exponent. 5 minus 3, we could also think about the fact that natural log is log base e, and we've got an exponent base e, so they cancel each other out. 4 over 5 minus 3, 4 over 5 minus 3 becomes 2, which equals 2. Hey, that checks out. So we can do it either numerically, or we can do it precisely and see that it worked in either case. All right, great. Now I've got a really good understanding of even probably the most complex kind of logarithmic and exponential equations that will be thrown at you at this point in math. So with this sort of knowledge, you can go forth, do all kinds of problems from the easy to the hard ones, and you'll be able to knock them out if you follow these things. And remember, be careful. Mistakes happen. You even saw one happen to me. So they happen to everybody. It's really useful to do these checks. By checking your work, you can make sure that you didn't make a mistake. And if you see something went wrong in the check, you can go through and carefully analyze your work and figure out where things went wrong. All right, we'll see you at educator.com later. Bye.